Alright, this is the next page. So, in order to be in compliance with this idea that they want to get as far away from each other as possible, this VSEPR theory, then they take various shapes. Well, if it's just AB, two atoms that are bonded together, that would be a linear shape, and we'd say the bond angle would be 180 degrees. If it was AB2, and there weren't any lone pairs, it would also be 180 degrees, be linear. If we add lone pairs, then the geometry would change depending on the number of lone pairs. If there was one lone pair and two bonds, it would be 120 degrees. If there were two lone pairs, which is more often the case, and two bonds, AB2, then it would be 109 degrees. We'd call that a bent shape. If we go to AB3, no lone pairs, that's going to be a trigonal planar, so that's going to be 120 degrees as our bond angle. And if we go to AB3, that's going to be trigonal pyramidal. Both trigonal pyramidal and tetrahedral will have bond angles of 109 degrees. Then, when we run into this term called electron geometry, that's just what the term used for if we were to consider the lone pairs as not just determining the shape, but what shape would it be counting those lone pairs as though they were a bond. Well, then can you see how if we count those lone pairs here in AB3 with one lone pair, even though we say that molecular geometry is trigonal pyramidal, if we factor in what it looks like with the lone pair considered to be a bond, then we'd call that a tetrahedral, the three bonds plus that lone pair. So, hopefully that's not confusing. But the truth is, I don't think we need to know anything about electronic geometry for our exam. We'll see a little bit, I think, on the final. I didn't give you all the structures here, but you can reason these out. So, water is going to make two bonds. Oxygen is going to have two lone pairs when we compare the electronegativities. Oxygens is 3.44, subtract hydrogens, which is 2.10. We get a difference of 1.34. Generally, when that difference is greater than 0.4 or 0.5, we'll draw on a dipole. That dipole means that oxygen is going to hug these electrons closer to it than hydrogen will, and that makes oxygen more negative and hydrogen more positive, so we call that a partial negative and a partial positive, because the bond will be polar. In terms of the whole molecule, if we put ourselves in the middle, we'd move up. Even though the molecule doesn't move, it just means this region here is going to be concentrated as a negative charge, and this region around here is going to be somewhat positive. That is going to have huge implications on how water behaves, and we'll get into that on the next page. Here's hydrogen, just H2. To satisfy the octet rule here, we need to have two double bonds, because silicon would be 1, 2, 3, 4. So we'd have two going one way, two going another. When we clean it up, it's going to be nice and linear. There aren't any lone pairs to bend it. This is a more unique one. We got to have, to satisfy the octet rule, we have to have 1, 2, 3, 4, 5, 6, 7, 8 electrons shared. So that's the only arrangement that would do that here. We'd have offsetting dipoles between bromine and carbon. So it would be a linear molecule that would be nonpolar. Here's BH2Br. So boron is one of those atoms that tends to make three bonds, and as a result, not satisfy the octet rule because there are no lone pairs. Consequently, it'll take a trigonal planar shape. There aren't any dipoles between B and H. You can see that they're very similar in their electronegativities. B is 2.04 and H is 2.10, so there's no dipoles here, but bromine would hog those electrons, making the molecule slightly polar.